So for our first example, we're going to use Gaussian elimination to solve the system 4x plus 2y equals 8 and 3x minus 2y equals 6. And to be clear, we have seen this example before. This is the one that I did at the very beginning, and you don't really need matrices to solve this one. It's pretty easy as far as these things go. But just to be sure, we're going to see how this can work using something that we know does work. And I'm going to say that with this stuff before I get into my process here, how I approach this example. Understand that when it comes to these, you can think of them as being like puzzles, where you can start from the outside edge and work inward. You can be a crazy person and start from the inside and go out, or you can just take pieces wherever they work and build them together as best you can until you're done. That is to say, there isn't just one way to approach this kind of problem. There isn't just one way to take the elimination procedure. I'm going to show you one way here. Sometimes when you have these, it's pretty obvious what you want to do. Sometimes, like with this one, it's not so obvious, and there are a couple ways to go about it. Here, if you want to work with that matrix and you want to get it to row echelon form, that means you want to get ones in there. And to get ones in there, I'm going to do something that's not plain to begin with, but you'll see that it helps out a fair amount. So what I'm going to do is I'm going to take the system first and turn it into a matrix. Step one, that's what you always have to do. And then step two, do most of the work. But the first operation I'm going to take is I'm going to look at that second row and see that if I add it to the first row, just like elimination where we started with, the method that you're probably most familiar with for using for this type of problem, although a lot of people like substitution more, but yeah, whatever. Point is, if you want to take care of that, you can just add up. You can do row 1 plus row 2. Pretty basic operation that we can do up there. And what we'll end up with is that second value in there, the coefficient for y, the 2 in the first row, will be removed. And from that, we can then take another fairly basic operation. What we can do is take our pieces there and divide row 1 by 7. That is to say, we multiply row 1 by 1/7. And actually, let me add just a tiny bit up here so I can make the picture a little bit cleaner. So in that first step, what we do is we take row 1 plus row 2, a basic combination. That's the word I'm looking for. Operation, excuse me. And then in the second step, we use the constant multiplication operation. Multiply 1/7 times row 1. And then in the third step, now that we have a 1 in that first part of the diagonal, and we have a 0 in the second part, which is nice but not necessary, we then take the pieces that we have for row 1 and use them to get rid of that part that's blocking row echelon in the second one. That is, we're going to take row 2 minus 3 times row 1, because we have a 1 in the first entry, the first element of row 1, and we can use 3 of those to get rid of the 3 in the first one for row 2. And that'll clear up that problem. And then from there, I'm going to have to erase a little bit because there's not enough space on my board for all of the work I need. Where for that next one, we're basically there, but we just need to take care of the fact that in that second part, in the second row, we don't have a 1, we've got a -2. So we're just going to get rid of that -2 the same way we got rid of the 7. We're going to multiply the second row by -1/2. Multiply 0 by -1/2, nothing happens. Multiply -2 by -1/2, and it becomes 1. And then on the other side, we've got that term on the other side. So what we'll be left with the simplification there, is a matrix that we can see up there with 1, 0, and 2 in the first row, along with 0, 1, and 0 in the second row. And think about what that looks like in terms of a system. we can understand that that's what I'm looking for. 1 corresponds to a coefficient of x that is 1. So there's an x. That 0 can be thought of as 0 y's, and then a 2. So we get x equals 2, and then in the second part, for the same reason, we get y equals 0. So just like expected, we get the solution, 2, 0. Same thing that we would have done before, except, well, we made it a little more complicated. But sometimes it's necessary to show a bit of work with something that we know will work, for the sake of seeing that the process does work also. I said work too many times in that sentence, but that's okay. Anyway, here we get our solution, and we actually don't need to do any substitution. This is because of the special way that I approached it, which technically is a bit of a subtle way to approach it. As you work with these, you'll see better and better approaches, but really, like I said at the beginning, there's lots of ways you can handle it. Anyway, this, where we have 1s and 0s, 1s on the diagonal and 0s everywhere else, except on the other side of the augmentation, that's what's called reduced row echelon form. It's a bit more powerful than row echelon form, and it's what I'll talk to at the end of this section, because it's a little cleaner. You have to deal with the substitution, but it also means a little bit more work, and sometimes, as we saw with this example, it's not always obvious about how you can go about, geez, my words, getting there.